And welcome to 90 Notes. Well, here we're going to explore the properties of a parallelogram by plotting one. And we'll just verify these various theorems, these four theorems, and the definition you heard earlier today. Starting with the most basic, the definition. Both pairs of opposite sides are parallel. Um, well, I guess we should plot this thing first. Let's start here. S in the third quadrant, -4, -6, and T, -2, +4, right there in the second quadrant. In the first quadrant, 10, 8, and down here the W8, -2. Oh, I missed. So you could take your Sammy straight edge and you can connect the dots. Yes. Oh, that looks nice. Now, we're going to demonstrate that the opposite sides are parallel first by, well, just finding the slopes. Go ahead and find the slopes. We know this boring formula, but we also know just intuitively rise over run. Now, sorry, my custom tools may get in the way, so let's say rise over run. I could visually represent that by going up and over. That's really what you're doing with your rise over run. You're saying how much of an increase, and it looks like a rise, that green arrow of 10 and over 2, and that looks like a slope of, well, up 10 over 2. No, ST, I got it over here. And you can simplify this, and of course up 10 over 2, and that would be a slope of 5. And I'm sure we're going to find the same thing for WV. Well, okay, well, let's just do it. We're going from here to here, and again, a positive slope. And we've verified right there. We've got the same slope. I'll just represent this one as 5 over 1. Same slope. Well, that's all right. I guess right there, that gives me the right to put in some little arrows there. I'm going to mark an arrow from here to here. So you could mark these two are parallel because those two lines have the same slope. Maybe I can get rid of some of these marks because they'll take over the drawing very quickly. Now, you're certainly welcome to do it the old school way, use it, do the formula, but let's say you're going to do this again. You're going to go up 1, 2, 3, up 4. That's a rise of 4, and this is a run. Remember, it's 2 just to get here, and a -10, up 4 over 12. So again, it looks like a positive slope. So TV up 4 and over 12. I'm sure you can simplify that, and you could use the formula, and either way, you're going to say, well, golly, it looks like it's got a slope of 1/3. So again, you can do the rise over run thing, but well, I suppose you could do it that way, or you can go back to your formula here, but verify that those two slopes are the same. So I got a slope of 1/3 there. I've got a slope of 1/3 there. And that's the very definition of a parallelogram. Both pairs of opposite sides are parallel. Now, one of the properties we have is that both pairs of opposite sides are congruent. We know the distance formula, and well, by now you've been exposed to the fact that it's the same as Pythagorean theorem, but there it is this way. Sometimes we write it like this. I like it better this way. And that's not triangle, that's the Greek letter delta, change in x, change in y. So if I were to look at this one, if I'm just looking at this right here, from S to T, we already know that it's got a horizontal change, or a change in x of 2. So I'm just going to say that's 2 squared. And in this case, the change in y, what is the change in y? That's the vertical distance, and we already mentioned that that was going to be 10. Now, I guess we could do the arithmetic there, and we know we've got 2 squared is 4, 10 squared is 100, and that's all said and done, that's going to end up be 100 plus 4, 100 plus 4, or the square root of 104. Well, let's see how this one comes out. VW or WV. Again, we've got a change in x of 2 and a change in y of 10. And of course, that again is going to come out to be 104. So those two are the same. And we could put in a little Timmy tick mark. Let me see if I got a side tick mark right there. There. Mark them congruent, because they are. TV, well, let's see what we got here. I've got a vertical distance, or the change, or let's say a horizontal distance. The change in x, the change in x, that is the distance horizontally from here to here. Well, I can see that's from 8 to negative 4. That's a distance of 12. So I could say the distance of the x is squared. Oh, I'm sorry, I guess I was doing WS, which hopefully will come out the same. And the vertical distance would be the distance from here up 1, 2, 3, 4. And that's a vertical distance of 4. Well, let's see if we can simplify this. We know that 12 squared is 144. And 4 squared is 16. When I take 144 and add 16, I should get, well, you guessed it, I should get 160. Go ahead and see if that works out the same for TV. I bet it does. And when you find that, then you can put in some little tick marks there. Like this, congruent to this. There we go. So now we're rolling. Now, as far as the angles, well, we're not going to do trig on this. Instead, let's just bring out your poly protractor and let's measure these bad boys and see if you can measure them plus or minus, a few degrees. Now, if I take this, oops, and I'm trying my best to measure this, and it's looking right there like 60. Do you think so? Yeah, I hope so. So it's looking like the measure of angle S is 60 degrees. That's as near as I can tell. You may have better eyes and a better compass. Again, make sure the vertex of the compass goes right there on the S. And then you're going to measure the opposite angles. I guess we have to measure these as well. We've got to measure these adjacent angles. And I can hold the protractor this way, like this, or I can hold it down here like this. Either way, I'm measuring it here. And I think now I'm measuring on this side of the scale. And that looks like a nice 120. So go ahead and measure that up, 120. That's what I'm getting. Let's see if you can get the same for the last two angles. You verify that. Let's see if you get angle V if you also get 60. Now this would verify a couple things. That the opposite angles S and V are congruent if they measure the same, and that the adjacent angles, in this case S and T, are supplementary, 60 and 120, and that would make 180. Hey, we're almost done with our demonstration, but the last thing we need to do is we need to draw those doggone diagonals. Snap. And I'm going to put them there, and I'm going to put them there. Now, we can see that these diagonals intersect at a point there that I'll call M. And, all we got to do is use the distance formula in each case. The distance formula, not the distance formula, the midpoint formula. The midpoint formula is the average of the x's, average of the y's. So let's take a look at this x right here. It really says what's in the middle. I'm going to take ST. Or SV. So we're looking at this diagonal, and then we should repeat it for TW. And that'll be kind of cool, and it should end up in the same spot. and we'll verify this. We'll say, well, s is -4, x1 is -4, and x2 looks like, well, that's going to be +10. So -4 plus 10, and divided by 2. And the y, this is going to be -6 over here. And this looks like 5, 6, 7, 8. That's 8. And heavens to Murgatroyds, you know it's going to come out. I'm going to make a copy of this, cut and paste, so we can just work this out. We know that -10 or -4 and 10 is 6. And that's going to be 6 over 2. This is going to be 2 over 2. And what do you know? That means that the coordinates of the midpoint, of this midpoint, are 6 over 2, 3, 1. Well, let's just change that to whole numbers. The coordinates are going to be 3, 1. And what do you know? 1, 2, 3, and up 1. So the intersection came out exactly at the midpoint of SV. Now you can verify that for yourselves as well with taking the points for T and W, because it'll be the midpoint of that segment as well. Okay, geometers. Well, that was a good little warm-up activity. So time to get on to the lesson. Thank you for watching Nani Notes.